Okay, section 6.5, part 1, we're going to look at partial fractions. So I think that this is something that you haven't done before, but if not, anyway, we're going to go over it. So, partial fraction, this says partial fraction decomposition with distinct linear denominators. So if we have a function that is a fraction where p and q are both polynomials, when the degree of p, the numerator, is less than the degree of q, or if q of x can be written as the product of distinct linear factors, then the function f of x can be written as a sum of rational functions with distinct linear denominators. That probably makes absolutely zero sense. So let's look at what we're talking about here. So if I have a polynomial function, for example, 3x minus 4 divided by x squared minus 4x. And if I can write this as a fraction where the denominator is distinct linear functions. So I've factored the denominator into two linear functions, x and x minus 4. I shouldn't really put an equal sign there. I now can take this function, okay, which I've rewritten in the form I need, and rewrite this as two separate fractions with new denominators where each fraction has a single linear denominator. This is going to allow us to integrate much more simply. So let's take a look at this problem that we're dealing with here. So looking at this, if I multiply both sides of this equation by my denominators and multiply this side by x times x minus 4, this side just becomes 3x minus 4, and distributing, multiplying times the first fraction, the x's cancel, and I have a times x minus 4. When I distribute over the second fraction, the x minus 4's cancel, and I get bx. So let's continue to expand this. 3x minus 4 equals ax minus 4a plus bx. I'm going to gather my x terms together on the left, and I'm going to write them as a single coefficient, a plus b times x minus 4a. We can now see that I'm in the same kind of pattern as I am on the left on the right. So the coefficient of x has to be 3. That means that a plus b has to equal 3. And the constant is negative 4. So negative 4 has to equal negative 4a. So solving for a first, I get a equals 1. Substituting in, I get 1 plus b equals 3, so b equals 2. Therefore, my original fraction, 3x minus 4 over x squared minus 4x, can be rewritten as a, 1 over x, plus my b, 2 over x minus 4. So let's take a look and see what this does for us. If you were being asked to integrate 3x minus 4 over x squared minus 4x dx, if the derivative of my denominator was the numerator, I could use u substitution, but I can't. So if I separate my variables, separate and create partial fractions, and go back to my 1 over x plus 2 over x minus 4. Now, I don't know why that line keeps popping up on me. Now I can separate this and take the integral of 1 over x dx plus the integral of 2 over x minus 4 dx, and this becomes ln of x plus 2 times ln of x minus 4 plus c. I can simplify this further. I can say ln of x, ln of x plus ln of x minus 4 squared. I don't need absolute value anymore because anything squared is positive. Using my product rule, I have ln of x times x minus 4 squared plus c. All right, let's try another partial fraction separation. So if I have something like this, 6x squared minus 8x minus 4 over x squared minus 4 times x minus 1. In order to get distinct linear denominators, I need x minus 2, x plus 2, and x minus 1, so I need a, b, and c. So let's again look at what we did before, multiplying both sides by the common denominator. 6x squared minus 8x minus 4 equals a times x plus 2 times x minus 1 plus b times x minus 2 times x minus 1 plus c times x minus 2x plus 2. Now I could FOIL this all out and get a big long polynomial with coefficients for x squared, x, and negative 4, but let me show you another method. I'm going to take each of these linear factors and one at a time put in a number that will make one of them 0. So starting with x plus 2. And I'm going to say if x equals negative 2. So on the left side I have 6 times 4, negative 2 squared, minus 8 times negative 2 minus 4. If I plug in negative 2 here, this all becomes 0. The last term all becomes 0, and I'm just left with b times negative 4 times negative 3. So on the left I have 24 minus 16 minus 4 equals 12b. This becomes minus 20. What did I do? Oh, that's plus 16. I knew that wasn't right. So now I get 36 equals 12b, and b equals 3. I can now do that again if x equals, I'm looking at this factor now, if x equals 1. So on the left, I would have 6 times 1 minus 8 times 1 minus 4. This becomes 0, the b becomes 0, and I have c times 1 minus 2 and 1 plus 2. So 6 minus 8 minus 4 is negative 6 equals negative 3c, and c equals 2. And I can do it one last time using x equal to positive 2. On the left, that would be 6 times 4 is 24, minus 16 minus 4. On the right, the only term that is left is my a's, because the b's and c's are multiplied by 0. So I have a times 4 times 1. On the left, 24 minus 20 is 4 equals 4a. So a equals 1. So my partial fraction here, back to my original problem, 6x squared minus 8x minus 4 over x squared minus 4 times x minus 1 equals what? Ooh, sorry. Let me see if I can get back. Okay, sorry about that. So my a value was 1 over my x minus 2. My b value was 3 over x plus 2. And my c value is 2 over x minus 1. And again, I could integrate that fairly easily. I'm also going to show you a method called the thumb rule or the cover-up rule. Don't let me forget to show you that in class. The last thing we want to look at, Let me go ahead and erase this. Oh, shoot. Alright, well, let me see what I can do here. I've made a mistake on my slide, and I don't think I can get rid of this now. Let me see what I can do. Bear with me. Let me see if I can get this to continue to work and get another screen in here. I'm sorry, be patient, be patient. I'm going to get there. I'm going to end the show. I'm going to come in here and try to add a couple slides. Okay. Let me see if I can keep going. Okay, let's try this. Sorry about all that. I made a mistake in creating my slideshow. I didn't have enough slides for myself. What if we want to try to do partial fractions with 3x to the 4th plus 1 over x squared minus 1? This does not follow our rule of the numerator being a smaller power than the denominator. So we're going to do some long division. 3x to the 4th plus 1 divided by x squared minus 1. Long division, x squared goes into 3x to the 4th, 3x squared times. Multiplying 3x squared times this, I get 3x to the 4th minus 3x squared, and I'm going to subtract. Those cancel. I don't have anything to subtract this from, so I'm going to subtract 3x squared, bring down the plus 1. I can multiply this times negative 3. Negative 3x squared plus 3, and again subtracting, I get negative 2, which is negative 2 over x squared minus 1. Nope. What did I do wrong? Negative 3 times negative 1 is plus 3. That's right. Okay, so now, no, I definitely did something wrong. I'm confusing myself because I lost track of my slide. 3x squared. Oh, that should have been a plus 3x squared. There's where I went wrong. When I subtract a negative, I get a positive. That makes this a plus 3. That makes this a minus 3. And subtracting then plus 1 minus a negative makes this plus 4. There we go. All right. If you're confused by that, ask me to do it again in class. Again, my apologies. But there's my polynomial. Now, all I have to get a partial fraction for is the last piece. So I'm going to look at my 4 over x squared minus 1. I'm going to put a over x minus 1, b over x plus 1. So multiplying everything by x squared minus 1, I get 4 equals a times x plus 1, b times x minus 1. 4 equals ax plus a plus bx minus b. So I've got a plus b as my coefficient of x and a minus b as my constant. A plus b has to equal 0. There is no x term on top. And a minus b has to equal 4. So if a plus b is 0, a equals negative b. Substitution, negative b minus b equals 4. Negative 2b equals 4. And b equals negative 2. Plugging back in here, if b is negative 2, then a is positive 2. So my final decomposition is 3x squared plus 3 plus my partial fraction A is 2 over my x minus 1, and B, oh my goodness, this slide is driving me crazy, is negative 2 or minus 2 over x plus 1. So that's my final decomposition. So we're going to do some of these and use them for integration. I will redo any of these that you need me to, since my slides went a little bit crazy, but you've got the general idea and we'll work on this together in class.